Hi there, I'm Nick Lauer, a biochem student of the class of 2018. Today we'll be going over problem 8 from chapter 11.4 in the General Chemistry Workbook. This is the problem. If you haven't already attempted it, please pause the video now and try it for yourself first. If you have trouble with the problem, please come back and watch the rest of this video. Now that you've attempted the problem yourself, let's go through it together. The radiator in your car holds 5 liters. Living here in sunny Central California, you don't often have to worry about the fluid in your radiator freezing. But suppose that you were a skier, and you frequently go up to the Sierras for ski weekends. If you want the fluid in your radiator to be safe, i.e. the fluid won't freeze, down to 20 degrees Celsius, how much ethylene glycol and water in liters must you put in your radiator? The density of ethylene glycol is 1.115 grams per milliliter. So there was a lot in that paragraph, and it was kind of all over the place. So let's break it down into the important pieces. So we know that our total volume is going to be 5 liters. We also know we want our final freezing temperature to be negative 20 degrees Celsius. We also have the density of ethylene glycol. Now what we're looking for is the volumes of ethylene glycol in water. So let's write this all down. So we have a V total of 5 liters. Now what we're looking for is the V of ethylene glycol, which I'm just going to abbreviate as VEG, which we don't know. We also want to know what the volume of water is. So we know that our final freezing temperature should be negative 20 degrees Celsius. We also know that the density of ethylene glycol is 1.115 grams per milliliter. So what this problem is actually asking us about is really just colligative properties. We're trying to figure out the freezing point depression of a solute in solvent. Luckily, we have an expression for this, and that is delta T of the freezing point is equal to I times the freezing point constant, or freezing point depression constant, multiplied by the molality of the solution. Now what we need to keep straight here is that this is molality and not molarity. And molality is the moles of solute dissolved in the kilograms of solvent. So then we need to ask ourselves, for this problem, which is the solvent and which is the solute? For this problem, the water is our solvent and the ethylene glycol is our solute. Since we know that water is our solvent, we just need to find out what the Kf for water is. Now we can just look this up in the table. So the Kf for water is just equal to 1.86 degrees Celsius per molality. Another tricky part of this expression is that I. So that I is just the dissociation constant, which, lucky for us, is just 1 since there's actually nothing dissociating. The last piece of this is the change in the freezing point, which luckily enough is just the initial freezing point, which for water is 0 degrees, minus the one we want, which is negative 20 degrees Celsius. So this just gives us 20 degrees Celsius as our change in freezing point. Putting this all together, we get an expression that looks like this. 20 degrees Celsius is equal to 1 times the Kf, which is 1.86 degrees Celsius per molality, times whatever the molality is. So just doing a simple algebraic manipulation, we find that the molarity is equal to 10.75 moles of Eg over 1 kilogram of H2O. Now this isn't really answering what the question wanted us to answer. Instead, we just found the moles of solute in the kilograms of solvent. However, with doing some unit conversions, we can actually convert this to a ratio of the volume of ethylene glycol per the volume of water. So our molality of ethylene glycol is 10.75 moles of ethylene glycol over 1 kilogram of H2O. Since the conversion of water into volume is a little bit easier, let's start with that one. So we know that the density of water is 1 gram per milliliter, but we have our mass in kilograms, so let's go ahead and convert that into grams. Now with our density of water that we just mentioned, let's convert that into milliliters. Now to convert ethylene glycol into a volume, we need to start with turning the moles into grams, so we'll need the molar mass. So let's go ahead and calculate that out. So the chemical formula for ethylene glycol is CH2OH, all of which is 2 times. So moving forward, we get that the molar mass of ethylene glycol is 62.08 grams per mole. The problem also gave us the density, so let's just go ahead and write that down here. So now we have all the elements we need to do this conversion, so let's continue. So we have the 10.75 moles of ethylene glycol, so let's convert that into grams. So we have the 62.08 grams over 1 mole, and then let's convert that into a volume with the density. So before we calculate this out, let's just make sure our units cancel. So we get rid of kilograms there, grams go away there, left with milliliters on the bottom. And then we cancel out our moles there, and we cancel out our grams here, and we're left with milliliters of ethylene glycol on top. The units all check out, so calculating this out, we get an answer of 0.5985 milliliters of ethylene glycol over 1 milliliter of H2O. Now, this only gives us a ratio, so to find what the actual answer is, we need to use our total volume, which we know is equal to the volumes of ethylene glycol and H2O added together, which we also know is a total of 5.0 liters. So since we have this ratio, we can just substitute one in and get that the total volume, 5 liters, is equal to 0.5985 volume of H2O plus the volume of H2O. Calculating this out, we find that the volume of water we need is equal to 3.12 liters. And the volume we need of ethylene glycol is just 5 minus this, which is 1.88 liters. So there you have it, our final answer, the volume of water and the volume of ethylene glycol dissolved in water. I hope this helped answer any questions you had about this problem, and thanks for watching.